All right, thank you everyone for coming to DLS this week. It's my pleasure to introduce Pablo Davila Harris as our speaker this week. Pablo is an associate professor in the Department of Applied Geosciences at the Instituto Potosino de Investigación Científica y Tecnológica in San Luis Potosino, Mexico. Pablo is visiting us for the year on his sabbatical. He's working in my group, and so he's here until May of 2025 with his family and his kids. So it's great to have them here for a long haul. Pablo earned his PhD at Leicester in the UK, and then went on and did a postdoc at UNAM in Ontario, that campus. At UNAM. Pablo's interests are really focused on the evolution of felsic volcanic sequences, which we're going to learn more about today. He's particularly interested in the processes and the products of explosive volcanic eruptions. And he studies this through a combination of field studies. This is actually how I got to know Pablo. We met in Cabo San Jose like 2 years ago to get on a boat to go to the Revillagigedo Islands offshore Mexico to look at felsic explosive volcanoes in the Eastern Pacific, and it was really fun working with a field volcanologist in a very young volcanic terrain. You learn a lot fast. But he combines field studies with argon, and uranium lead geochronology, a variety of geochemical methods, petrological methods, and paleomag. So he's here to practice some of those dark arts of paleomag in my group over the next year. But I'll be quiet and hand it over to Pablo, who's gonna maybe tell us about the geology and petrology of Ignimbrites.
Thank you. Thanks, Pete. That's great. Thank you. Thank everybody. First of all, I will have to thank you to the department and everybody to welcome me here for this time in Utah. That it's been wonderful so far, and I'm looking forward for the snow as well. So when I was thinking about the title, I said, I think I made quite a mistake, because actually the title, instead of from the crust to the surface, it should be the other way around, from the surface to the crust, because we study rocks in the surface and then we interpret what is going on the crust, you see. But then I realized that I made another mistake. And it's actually that the title should be something like this, rather than the geology and petrology should be my attempt to do. But this is actually in Baja Sur with a friend doing field work there, and a lot of colleagues. So, okay. Also, I will have to say that this is because the talk is being recorded, that this presentation is not only my work independently. As we all know, this is a group work, a collaboration with these colleagues from, at that time, he was in, Graham Andrews was in Santa Barbara, and then he moved to West Virginia, and other colleagues for the Sierra Madre Transect that I'm going to talk to you today, and another work on the Sierra Madre Paleo Elevation Project, and also on the Geology of the Ignimbrites with Aaron Martin and Maggie Fan, and a couple of master students and PhD students, and also other collaborations in other parts that we are going to talk about today. This is the outline of the presentation, just a quick introduction to the Ignimbrites and the origin of Ignimbrites and explosive eruptions that most of you probably already know. Some basic on Ignimbrite emplacement, some type of questions we want to explore, and a couple of examples mainly from the Sierra Madre, and then other ones from elsewhere. Why Ignimbrites? Well, Mexico its territory is about 75% volcanic rocks, and a lot of them are actually silicic volcanic rocks on the western part of Mexico, northwest Sierra Madre. This voluminous volcanism is not very well understood yet, although we've been working with that a long time. Questions like, are we adding to the crust, or are we just melting what is underneath, are important, so we can learn more about this large province. What are the climatic effects of these large eruptions in the continent, and the eruption mechanism of these large silicic provinces is also not very well understood. And something really important is that that province is full of mineral deposits, and at this time is also being explored for their possibilities for geothermal prospecting. So ignimbrites. Ignimbrites, we need explosive eruptions to form ignimbrites. So first of all, we want to check, I would like to talk about something for what's going on in, I'm not very familiar with this pointer. Okay, what is going on here, that is actually the part where ignimbrites are formed on the surface. So if we remember our volcanology classes here, we have magma reservoir, the conduit. This is where fragmentation takes place. If we remember Michael Manga's talk last month, we have the fragmentation, the solution, the exhaust volatiles that go up into the conduit, and then we have the jet phase, the convective phase, and the umbrella region, which is actually a very simple definition of the eruptive column. We have either vertically direction of the gases and materials, or either sometimes lateral. It's composed of volcanic ash, pumice, lithics, and also some droplets of melt or pieces of glass, loose crystals, and country rock that comes from the wall rock of the conduit or of the vent. So that's mostly the basics on an eruptive column. But why is important for ignimbrites? Well, if we see, this is a famous photo of Etna in 2015. You see that the cartoon is not that wrong. We can identify the thrust or jet section here. We can see the convective part of the column and the umbrella cloud. But then not always this type of explosive eruptions produce ignimbrites. So what do we need for in our geological record or in our volcanoes to produce this type of geological record? Well, first of all, we need huge parcels of magma fragmentating when it's going up to the surface. So fragmentation is probably the most important process that drives explosive eruptions, and then again the emplacement of ignimbrites. Fragmentation is, in a simple way, it's just a transition from a continuous melt here, like the red is the melt, with a discontinuous dispersed gas phase. And this changes towards a continuous gas phase with discontinuous pieces of the melt. And that is, in a nutshell, a very simple way to see fragmentation. So if we go back to the eruptive column cartoon, we are going to concentrate on this part, because it's actually where the ignimbrites, or where the column changes towards forming an ignimbrite, a volcanological process that produces an ignimbrite. This is the gas thrust. The gas thrust, the numbers are just amazing. These are, of course, from the literature. It can be 100 meters to 1,000 meters on top of the surface. Is where the expansion of aromatic gases occur. But look at the velocities. It can go 100 meters per second up to 400 meters per second in Plinian eruptions, like the ones at, for example, Mount St. Helens and Pinatubo, and so on. But what happens when changes happen? For example, the eruption slows down. It loses influx, magma influx. It loses energy, momentum, or something like water within the system changes, or even collapses down the conduit. Then that's when we produce this. And this is a concept that is being in the volcanological literature for a while. And this is the famous concept of column collapse. But a question I will ask you here: do you see really that the column is collapsing? Not really. I mean, the complete column does not collapse, or apparently, at least in this example. And that kind of works for most of the columns. So what happens is actually that when the jet cannot incorporate enough air into the system, then the buoyancy of this part of the column sort of stops there, and the velocity of the plume equals like 0, and the rest of the atmosphere, and it gets much denser, and just the column cannot go up. And so the trajectory of the ashes, instead of going up, is just starting to fountain, like doing fountain trajectories. And that's when column collapse occur. But most of the time is a partial column collapse. So the material is still going up where it can, but some other part is just going laterally, and that's when ignimbrites form. And the result in the field is something like this. We have a sequence here that is actually quite a very well studied one in central Mexico. This is the Nevado de Toluca pumice fault deposit. So you get, going back to the column collapse, you can get pyroclastic density currents that produce the ignimbrites either from partial or complete collapse, from the direct formation of non-buoyant plumes, or boiling over, which is very common in calderas, directed blast, like the example in Mount St. Helens, that is here in the US, and the small ones like dome collapse that produces very, very small pyroclastic flows. So why is that ignimbrite? I'm going to go back to this. Why is that ignimbrite? What is that important for us that we study ignimbrites now in the field? We don't really get much into active volcanoes because you cannot go there when a pyroclastic flow is happening. So you wait that it happens and then just go there, or study the ones that are like 20 million years. That's what I'm doing actually. So you have the fault deposit at the base. You see, this is ash, pumice fault that fell down at the early stages of the eruption. But then you have the onset. These lines mark the onset of the pyroclastic flows, but the pumice keeps falling down. And then you have another deposit from a pyroclastic flow, and the pumice fault deposit keep falling down. But as you see, it looks like budins here that is being removed by the pyroclastic flows that passed by. Some of them passed by, some of them managed to deposit this part that was actually the climatic or the paroxysmal phase of the eruption. So that way you can sort of identify or solve the inverse problem of the eruption with the deposition of the ignimbrite in the field. That is actually quite fun. Not in all cases you can do this, but in some. And what is an ignimbrite? Most of you know what is an ignimbrite, but it's just as a simple deposit, as a simple definition, is a pumice-rich deposit. You see the pumices here, which are actually rounded. This is like the basic massive lapilli-tuff that can be found anywhere in a volcanic terrain when they are not welded. And is formed by ash in the matrix, broken lithics, crystal glass, and is very poorly solved because you have material from all types of sizes. In the early stages, geologists did fantastic work trying to define the standard ignimbrite flow unit. And they thought that most of the ignimbrites behave like this, with a front, with a surge front, and with a denser flow that was coming behind, and then a buoyant plume that was actually on top. So when they used to see an ignimbrite in the field of 20 meters, they said, oh, that probably the pyroclastic flow was 40 meters high. And they had these sort of ideas. And they end up with this classic ignimbrite flow unit that it worked really well all the late 70s and 80s, where they have a ground layer, a basal layer, and then a lithic concentration zones at the base, then some elytration pipes at the middle of the deposit, and a pumice concentration zone, and the co-ignimbrite ash cloud here that was depositing at the end of the eruption. And it worked for several ignimbrites, they moving around. But as the more they knew, then they start realizing that it was actually not working for most of the ignimbrites. Well, were not behaving like this. So At the late 90s, early 2000, Mike Brani and Pete Coquelard, based on actually some classic sedimentological studies from the density current, from the turbidity current works, they came up with this new model called the progressive aggradation model. That it's a very simple one, and it only instead of identifying the flow that is actually deposited en masse, like a plug flow, they intend to understand these flows as an aggrading material that is just building up upwards as the flow moves. So this is just, as in a cartoon, the aggrading ignimbrite here, and this is the paraclastic flow or current that is moving, and some parts of the current are depositing, some parts are just bypassing. So not, and that is actually really, really interesting, because when we go to the field, and if you remember these photos of the ignimbrites, the only thing that actually when you see an ignimbrite in the field, and you put your finger on the rock there, it's telling you what was happening at this part that is actually the flow boundary zone. And this flow boundary zone is the uppermost part of the aggrading ignimbrite, or the deposit, and the lowermost of the flow. And that is actually when things are happening. But that zone sort of migrates through time and the space where the paraclastic flow is moving. And if we do like a zoom up to this boundary zone, we can see this is the upper part of the deposit, and this is the basal part of the current. Here is a concentration profile with just no scale, high concentration, and low concentration on the base of the flow, because this is already a deposit, you see, and this is the flow. And then this is a velocity profile. Velocity here is 0, but then as you move up to the flow, the velocity increases. And this sharp interface sort of is what produces, for example, stratified ignimbrites in the field. And if this interface is not that sharp, then you produce massive ignimbrites. And that actually works really well when you try to interpret these structures in the field using these type of models. In this one, for example, you see stratified ignimbrite at the base, and then massive here. But then as you move laterally, you see some splay and fade structures that will be actually not very possible to form if you have a plug flow. The same operates, for example, this one, where you have stratified white fine-grained base eroded by the current that was actually bypassing and scouring on the previous deposits form. And just a last example, just to make, for example, in the past, we used to interpret these large blocks or large boulders in ignimbrites like floating, like they came floating with the paraclastic flow. And if you are, for example, this is around 70 kilometers from the source, it's difficult to think that this mixture of gases and lithics and ash can actually sustain lithics that are 20 kilos or 50 pounds or 100 pounds in weight. So they were just like in our basic sedimentology, they were just saltating or just floating, not floating, sorry, they were just, in saltation, but not in suspension. So there was some material in suspension, yes, but not the heavy loads. Those were actually deposited. Here was the surface at the time of that flow boundary zone. Okay, so that's sedimentology of ignimbrites. And the interesting thing is that we can reconstruct that behavior with of the paraclastic density current with the deposit that we have in the field. And if we translate this onto chemistry, then it makes things really interesting. You see here, this is the Acatlán ignimbrite, a cartoon from an ignimbrite that actually George Walker worked in the early 80s. And it's a zone ignimbrite. It has different composition at the base. The blue is, for example, sort of andesitic ignimbrite, and then it turns into more dacite, rhyodacite ignimbrite at the top. And they used to see these sections, and they used to interpret these as different deposits, you know, through time. But it's actually the same ignimbrite, just varying through time. Because they said, oh, but why you don't have the full composition range in the other side of this gully or whatever? Because ignimbrites just through time the current was depositing different compositions through time that didn't reach that far, for example. And this helped a lot this model, and it's important because we have formation of these. This is a classic photo of the Mazama ignimbrite here in Oregon. I would like to have not been there, so that's not my photo. I would like to be there once I'm here, not too far. You have other examples in the literature, like the Arico ignimbrite in the Canaries. You have some ignimbrites in the Sierra Madre, and so on and so forth. And then we come, volcanologists, and try to do petrology and come up with these very fancy diagrams and try to make cartoons of the magma reservoirs. And this is a great example, actually, from a paper by Jorge Romero in the Andes, where they reconstruct the conditions of the magma chamber prior to a sector collapse in the volcano, and then what happened after the sector collapse. And they do all this sort of reverse problem, solving it through the deposition. And one that is actually the favorite one for not only Italian volcanologists, but volcanologists elsewhere, is the Campanian ignimbrite from the Campi Flegrei. I think they have, I don't know, 2 or 3 papers per year. It's just been giving. And it's a really interesting eruption with a great zonation, chemical zonation. And most recently, while I was preparing this talk, I was looking at the literature, and I saw this work by Teresa Uvide. Probably Sarah knows her, and she's working with clinopyroxene and try to reconstruct the structure of the plumbing system through the chemical signature, microchemical signatures on the clinopyroxene zonation. And so this is just to show you the variation of ignimbrites. It kind of feels weird because when you talk about basalts, yes, basalts are usually very similar the chemistry, and texturally they just have more vesicles and less vesicles. And ignimbrites somehow, not that, I mean, the name is the same, but if you look ignimbrites in the field, they can look very different. Here I choose only non-welded ignimbrites, 5 examples from Mexico, and the color is very contrasting. But I don't have here welded ignimbrites, rheomorphic ignimbrites, lava-like ignimbrites, etc. So you either like structural geology, you can focus on rheomorphism of ignimbrites, for example. You like sedimentology, and you work with non-welded, and so on. Okay, the role in the geological record. So this is Northwest Mexico, the Sierra Madre Occidental with the Trans-Mexican volcanic belt is just full of ignimbrites and volcanic rocks, mostly ignimbrites in this region here, and also part of Baja California Sur. And then if we keep following on Sierra Madre del Sur, just below the Trans-Mexican volcanic belt, which is the active arc at the moment, you have also a lot of felsic volcanic rocks. In the USA, just a lot of volcanic rocks as well. This is only Idaho State, the Yellowstone hotspot tract, you know very well, Columbia River basalts, and a lot. These are all only volcanic rocks in Idaho. And of course, we have California, Oregon, all that. And Utah. You do have also some volcanic rocks, much more than this, but the Gately volcanics around here, Pete, correct me if I say this wrong, Marysville volcanic field around here, and there's also some volcanism, intraplate volcanism around the basin and range in the southwest, and I remember Stephanie told me about other possible calderas around here. So volcanic rocks are everywhere. So that's why it's interesting to study, you know. But yes, some examples here. You all remember these anomalous eruptions, Toba, or probably from the literature, magazines, whatever. Toba, Tambora, Ilopango, Snake River, Bishop, Bandelier. Most of these anomalous ignimbrites produce, anomalous explosions produce large ignimbrites. Most of them have not been formed by fissure eruptions or other type. They are formed by calderas or composite stratovolcanoes. What type of questions can we solve from these? Well, in active volcanoes, we can work their past eruptive behavior, the recurrence time, triggers, ascent paths, effects on society or climate. And in non-active volcanoes, we can do some of these, but we can do also some indirect tectonic settings that don't work at the moment anymore. We can do some magmatic processes with some limitations, emplacement processes, working with the deposits, and of course all the same geology relation again. And in what I sort of do as research is mostly this type of work here. I don't work much with active volcanoes anymore, but it's also interesting. So now let's go into the case study. This is a map of large igneous provinces around the world. You probably know already. In red, these are the continental fluid basalts. For example, the Columbia River, the Paranaetan Decca, Siberian traps, Deccan traps in India. In blue, the ocean basalt, fluid basalts, and in yellow, the silicic province, with some in Australia, ones in Patagonia, in the southern tip of South America, and here in the US, southern US, southwest US, and northern Mexico, we have the Sierra Madre Occidental and the continuation towards the. This is interesting because they should be more than 100,000 cubic kilometers in volume to be called a large igneous province. The area has to be more than 100,000 square kilometers, and with lifespans around 50 million years, and with pulses around every 1 or 2 million years of eruptions throughout. Let's go into the case studies. This is going back to Mexico now. We did the study, early to Oligocene changes in Ignimbrite and magma generation in the Sierra Madre. This is Popocatépetl, actually, so probably not very along with the subject of the study. It's just a nice photo. This is the Sierra Madre. You probably all know you have big mountains here. This is a huge terrain, but it's really understudied. So if we compare it with the Northwest Cordillera, we don't have as many geologists working here. So we have huge blank spaces through the Silicic province. It's the largest Silicic large igneous province in North America and in the Cenozoic. Is the largest, the third largest worldwide, and is contemporary with this the mid-tertiary Ignimbrite rock, and the volcanism of the basin and range is 2,000 kilometers long by 200 to 500 kilometers wide, and its estimated total volume is 400,000 kilometers. That's a volume. That's a lot of rock. See that was produced in less than 50 million years. This is a geological section of the Sierra Madre. The Sierra Madre has unextended core, is in pale brown, with extended lateral parts. In the north, it hits the southern basin and range. In the south, the extensional province of the triple junction here in the Chapala Rift. And then on the west is truncated by the extensional rift here in the Sea of Cortez. Another photo of how it looks, because because it's just nice. This is the central core. You see, is just a layer cake of ignimbrites, one after the other, just with not much tectonic, not extended, not tilted. But then as you move towards the sides of the Sierra Madre, you start getting a lot of faulting. How it was formed? It was formed by these flare-ups that I mentioned before. Here in the Sierra Madre are around 2 million years to 4 million year flare-ups. The earliest one around 46 to 42 million years, and then up to 38 million years. The most voluminous one is the one between 36 to 28 million year, with a volume of 300,000 cubic kilometers. But I've been working in these two more recent ones, the late Oligocene and the mid Oligocene. This is a compiled geological map of the Sierra Madre by Ferrari and collaborators, but there are still a lot of geology that needs to be studied in detail here. What are the main questions? So we have this huge province, but we don't have the volcanoes. We don't have the vents. Some hypotheses mentioned the calderas should be there, but they're going to be like in pieces, like for example in Marysvale. Don't see really calderas, or some of the calderas are actually not like the ones that we've seen in the past eruptions. They are just fissure or graben calderas, tectonic calderas that are not very well known. But the thing is that the ignimbrites are there, and they had to come out somehow. So we went to the field and we did 3 transects. This northern part of the Sierra, in green, has been studied a lot by the University of Texas group, Fred McDowell and collaborators. They've done a fantastic work there. We've done some work there in the central north part with the Parral Guadalupe Calvo transect, then a transect north Valleza and Huachochi, and a central one in the central sector that is actually the only highway that crosses the Sierra Madre properly. And there is also the southern bit that has been done some work by Ferrari and other colleagues. So I'm going to talk to you quickly about these 3 transects and some results. This is Google a satellite image of the northern transect. The central transect is 250 kilometers. This is a highway 24 that finishes around here. And you see this is the extended part towards the east, extended part towards the west, and the unextended core here with some basalts on the top, taking these ignimbrite sequences. The northern one is 200 kilometers long on highway 20. I think this was actually 20, not 24. Sorry, and it finishes here in Huachochi. There are no more roads that go west. Just a couple of dirt tracks there that you can follow. And that's why we just finished there, because there's just nothing else you can move around, and you can just not do. And you can do proper jobs. You need like a lot of PhD students, and masters and postdocs, and a lot of money, and probably a helicopter as well. But we have miners, and miners do like to do this type of roads. If you remember the talk last week, Moira showed us exactly a very similar road. So when we hit into the Barranca, we found this road, and we just went down and sampled. This is a huge Barranca. It's almost 1.5 kilometer high, the canyon, and we managed to do a strat column with sampling from the base of the river here, all the way to the top. So we had some good information, and this section was not done before. So we'll be probably I don't know, 80 years ago when people sampled the Grand Canyon here. Just probably saying wrong things, but anyway, we felt like that because miners go there, but they just go there and drill. They don't care they don't care much about the volcanology of the province. The top units, as I mentioned, is parallel ignimbrites. And then as you move down, you start seeing the blocks tilting. And you can see that you are getting into the extended part of the province here. This work has been already published in this paper. Most of this has been published. We did isotope geochemistry on zircons of 49 rhyolitic ignimbrites and lavas from those sections. And we did find some interesting things regarding the magmatic system there. We did some pair geochronology. Sorry for the table. We did some uranium-lead ages and some argon-argon. Oops, sorry about this. Where we have some residence times between the zircon ages and the feldspar ages. Is roughly 2 million years difference. And some results on the spatial distribution. We, in a summary, we recognize like a younging direction that is going towards the southwest. That is not new. It just supports previous interpretations in the north and in the south, and that actually fits well with the model that mentions that the arc was just retracting towards the west. Remember, this was formed by the Farayon plate subducting. This is the younging direction here. This is in this transect with some ages, roughly 39 million years to 32, with some outliers like old ignimbrites at the base of that huge barranca here, almost Cretaceous ignimbrites there. What was actually really interesting to see, and some correlation of the ignimbrites as well. Some ignimbrites that we recognize across 40 to 50 kilometers on for example, this one, the El Ojito ignimbrite, with volumes around nearly 100 cubic kilometers individually. Some findings, general findings. Mostly we have broadened the information of the Sierra Madre. We have new dates that are already there in the literature for helping to understand the province. The pair geochronology allows to understand better the residence time between the time that takes place for these rhyolites to produce and erupt. We have also information that reinforces this hypothesis of an east-west migration of the arc, and some correlation of ignimbrites. And finally, we moved on the central sector here, which is the Durango-Mazatlan, that is very well known because we had a few years ago a really nice tall highway built across here. It used to be a very bendy road, but now it's quite nice. So we have new road cuts, and for us was fantastic because we have new exposures. We have exposures like this that we can work just before they get covered in concrete by the owners of the highway here. So we went there and do some detailed samplings. I have to say that most of these units, the El Salto sequence, Fred McDowell and their colleagues, they've already done a great job there. But it was just too big that they sampled here and there. So what we were trying to do is sampling the units that are not recognized on their stratigraphic work, and also from other colleagues in Mexico. So we did more like a volcanology type of work rather than only geochronology and geochemistry. If we see the chemistry is very monotonous, the whole rock chemistry. We don't see much variation, just rhyolites and rhyodacite. So we jump into the mineral chemistry, and that's where we start finding some interesting things. We see variations within the chemistry of the feldspars in between these ignimbrites, because prior to this, everybody said, oh no, that's just a monotonous bunch of ignimbrites and rhyolites there that don't tell us too much. But we think that's not quite, and each volcano has its peculiarities. And we did some very simple statistical work on these feldspars, and we found some distribution across the units. For example, these are exposures of different ignimbrites or the same ignimbrite with different samples across. We did the same with biotites, and we do recognize some interesting clustering of the biotites from the older flare-ups and the younger flare-ups. So you can see that there is some, through time, some changes in the biotite composition, where the lower flare-up shows higher magnesium ratios, and the biotite with time becomes more magnesium. And also some geothermometry, of course, but we had to do it. And through time, we see that the biotites, their crystallization temperatures get slightly hotter, and that this is a Younging direction on the vertical axis. And with feldspars, we have surprisingly the opposite. We have some sort of the crystallization temperatures get slightly colder. And we had recognized for the first time compositional zoning, like the ignimbrites we mentioned before in the talk. We can recognize that in the Sierra Madre. That is something that hasn't been shown before. So we actually think that's quite cool. We also identify variations between fault deposits and ignimbrites, a very different chemistry that we can correlate doing isopachs and isoplets towards different possible vent sites. That is a big question there in the Sierra Madre. So just to wrap this up, the magma with time becomes less silicic. Younger eruptions tap magma bodies from deeper levels with less upper crustal processing. These changes suggest either also, these processes, slab rollback or breakage of the slab. This is not our idea. This has been documented before already, and we think this compositional heterogeneity is more common than expected. Okay, so just to finish, I'm going to talk you now. It's been a lot of ignimbrites to talk. I'm going to talk to you. This is actually where we went. This is the youngest of the volcanoes in the Revillagigedo archipelago. Is the Bárcena volcano, erupted in 1952 to 1953, and it formed a new part of the island. It was really cool, and we have some project going on. Hopefully, during this sabbatical, I can write the first draft. So we'll see. So other applications studying ignimbrites. We did a project here in Central America. This is San Salvador. This is the capital city. I have 5 minutes yet. This is the caldera of Ilopango caldera, which is a beautiful lake here, and it produced this the Toba Blanca Joven ignimbrite, which is a huge ignimbrite that covered a lot of the landscape here, and it also covered some Mayan ruins. So we think this was probably an eruption responsible to migrate the Mayan civilization towards the north, south of Mexico, for example. And in a paper recently of the group, we were able to trace the ashes of this eruption up to some ice cores in Greenland. So it was really cool. Also, we can use this type of studies to correlate for example, ignimbrites on the extensional province of the Gulf of Cortez that happened from 8 to 5 million years ago. So all the ignimbrites were already deposited, and this broke up. And there are a couple of studies that try to correlate, one here in Sonora, another one here in the south, but they use argon-argon ages, and even though they are really good ages, they are all within error. So you have 20 ignimbrites in that 2 million year span. So it can be just anyone, any other ignimbrite. So using this type of methodology can help us solve. And also it's an awful place to work, I have to say, there in Baja Sur. And some other examples that I'm not going to go into detail, but we also did some work with ignimbrites working in pseudokarst. This is the Humeros caldera, central Mexico, that produced a huge eruption in the Pleistocene that covered most of these canyons. These are all limestone Mesozoic canyons. The Ignimbrite filled up these canyons and then get eroded, and you have the formation of these caves within the Ignimbrite. You have flowstones and all sort of speleothems, but it was all correlated using this type of chemical studies. And that's it for me. Open for questions. Thank you.
Any questions from the students? Anyone else?
Thank you. So you said that you were seeing with Zircon and Crust isotopic analysis, volcanism becoming younger and younger, going south, which is correlated potentially to the retraction of the slabs.
Yes.
And you also did like a full stratigraphic column on the thanks to the road that was built by miners.
Mm-hmm.
So I was wondering if you were seeing any age difference between the top of this column and the bottom of this column that will give you some information of how many basically eruption happens to form the whole valley, or if that corresponds to only one single eruption.
Yes, that's a good question. And I actually canceled one slide that explains how I had to cancel a lot. Yes, we have dates from the bottom to the top. We have around 20 million years.
Oh.
Yes. Yeah, because we have some andesites at the bottom that correspond to the lower supergroup. Miners work with the lower supergroup of volcanism and the upper supergroup. And they think most of the gold and silver is in the lower supergroup, but we've proved that wrong now with the new ages. But anyway, that's another subject. But yeah, it's a 20 million year stack of eruptions with some hiatuses, and then you have a huge unconformity on the top, because then everything is capped, not everything, but in that specific section, and in others you have basalts, scorba basalts, equivalent to scorba, Southern Cordillera basalts and andesites that are around 8 million years or something, much more younger. So yeah, but in how many eruptions? That will be more than 50, probably less than 100 eruptions. Independent eruptions separated by paleosols or unconformities. Yeah.
So I thought it was Middle East, but I'm curious to know if you have any preliminary ideas on how explaining why the feldspar and the biotype show opposite trends of evolution of the temple.
I don't want to say this, but I think the biotite thermometry is not very well. If not I don't trust much those biotite results. I have to look further into that. Yes, we should probably discuss this because I have some doubts. Yeah, the feldspars are in equilibrium. Those are much better. But the biotites, it's an old thermometry. Is an old one, so probably I need to update my my analysis there. But anyway, they should. I mean, the question is, should they go hotter, both of them? We don't. I mean, we have to look. We have to look deeper into the ideas of the reservoirs, because you can be tapping different parts of the reservoirs. We now know that these are not just round reservoir magma chambers. These are more heterogeneous. So,
so just to follow up on that, do the Argon system, the biotite with sanidine ages agree? And the ones where you dated.
Yeah, yes, they were okay. Yeah. They were sort of similar. Not precisely. There was some difference, but not like, for example, with zircons. Yeah, the recurrence times is also a difficult thing to calculate. With a lot of work has done around 10 years ago with this, and probably before this. And we only did a very just normal calculation, and we came up with this roughly 2 million year residence times, but it can be plus minus.
So I'm actually less familiar with the silicic large igneous condenses in comparison to the internal flood basalt. And I noticed on your map that first there are not that many. And second, the actual cause for the flood basalt, for example, is still a very active debate. Like, is there a plume? Is there any active upwelling during the continental breaking or stuff like that? So what is the actual most admitted model for creating this large igneous silicic provinces?
Well, for people that study large igneous provinces, what I remember, it was that it was not easy to get slips within the lips, So silicic large igneous provinces within the lips, large igneous provinces, basalt ones. But then proving volumes and scales and all that, they said, okay, welcome to our group. You can join us. I'm not sure about the Australian ones and the ones in South America. But in this one, there's no, and I'm sure they are not related to hotspots or mantle plumes at all. They are related with anomalous situations on subduction environments. Yeah, or these rollbacks or these breakups and very rapid subduction times. Yeah, it's definitely something interesting to look at. Yeah.
You had mentioned just quickly one of your slides, and I don't study Ignimbrites at all, so I'm curious how you had said you found evidence of an ash emplacement all the way up in Greenland from one of these events. How did you guys deduce that? Was it is there some compositional?
Yes. Yes. This was a big group that worked here. I worked mostly with the Ignimbrite in the field. We sampled. First of all, we needed a high precision date because the Ignimbrite, the eruption is 430, the common era. But there were some other dates from offshore boreholes that were different. And then the archaeologists said, we have another date with our pieces of the pottery and things like that. And there was a discussion. So we had a fantastic exposure of a tree within the Ignimbrite, completely burned. It was very difficult to sample. We managed to sample, and Vicky Smith did some dendrite chronology, and she managed to get a really high precision age. Knowing that, then we went to look at the records at the ice cores, and we saw and there was at 430 there is a change on one proxy that is sulfur something in the atmosphere. I'm not very familiar with the concept, but it's SSM or something like that. And there is a peak there in these records at the same time. And looking at the cores, then we sampled the material that was there and get glass. And the chemistry of the glasses also correlates with the chemistry of the glasses here. So attaching that,
So they
it was.
match up the glass composition matches up.
Yeah.
Is that SSM proxy relates?
And
To gassing during these events in some way?
sorry again.
Yeah, I'm
Yes.
curious about this. I can ask you afterwards, maybe
Yeah.
about how the subject proxy relates.
Yeah, but definitely. I mean, that's a great question. It's difficult, and
Like you did a lot of things.
a model, and also some modeling on of the plume, of the dispersion of the plume. But it's not. I mean, with the Toba eruption, it's very well known that they have registered on the ice cores. It's not that you get thick beds of ash all the way there.
Yeah.
You have just tiny bits on the surface of the ice that can correlate with the proxies. And yeah, it's interesting.
I'll ask you. I'm selfish and I think about an element no one else does a lot, thallium. Thallium really likes to follow potassium. And so rocks that are potassium rich could potentially also be thallium rich. I'd be interested. Sounds like you've done extracurricular activities in some of your projects here. Have you ever measured thallium concentrations in these ignimbrites? I imagine the answer is no, but it's worth asking.
No, but thanks for the idea. We should do it. Yeah, but where, in crystals or in glass or?
So in potassium parts, you have a lot of thallium.
Oh yeah,
So
yeah.
there's processes that move elements in and out of potassium-rich rocks. You could also move thallium in that process. Thallium also has a really little boiling point, which also helps it become volatilized during some of these processes. But the sources of thallium to the ocean today, a lot of them are volcanic, but we don't understand quite how those operate in detail yet.
Mhm.
There might be some ways to plug
Oh, definitely. Yeah, definitely. Yeah, sure.
There are no more questions. We'll end a couple minutes early. If you think of other questions, feel free to grab Pablo Zero while he's here. He'll be here, like Pete said, until next May, and we're lucky to have him. So thanks again for giving us your.
Oh, thank you. Thank you. Thank you.